And today, for today, this is our table of content. Like you guys know that we are studying electromagnetic theory. Okay, and there were three parts. The first one was electrostate, second one magnetostate, and the third one related to the laws of electromagnetism, the basic theory of electromagnetism. Okay, so in electrostate part, we studied about Coulomb's law and Gauss law and their applications and varying electric fields, etc., polarization, capacitors, condensers, etc. In magnetic field, magnetostate part, we studied about the moving charge. We studied about the laws of Faraday and Lenz's. We studied about Biot-Savart's law and Ampere's law and their applications. Okay, so this is our third part of electrodynamics, ED or electromagnetic theory. Basically, this part have the equal weightage and at least one question in each paper always come from this part. So very important part, a very important lecture today. There were many questions to choose for this lecture, but I can't choose all the questions, and that is why I have put some most important questions in this lecture. So, related to those questions, we are going to study some theory. So, in this lecture, first of all, we'll introduce the laws of electromagnetism. Then we'll introduce Maxwell's equations in electromagnetic fields. Then obviously in Maxwell equation there is a concept of displacement current and displacement vector. So I'll tell you how displacement current is generated, and at last I'll tell you about electromagnetic radiation, and we'll do some question and answers. So here we are going to start. This is your electromagnetic spectrum. I hope the same picture you have seen a lot many times in your previous classes. So the electromagnetic spectrum having all the types of radiations, all the types of rays and waves which are presented in today's scenario of environment, from lower wavelength to the higher wavelength, from lower frequency to the higher frequency. When we observe this spectrum, then we are finding some reasons like some frequency range for radio waves, some for microwaves, some for infrared, some for ultraviolet, some for X-rays, gamma rays, etc. And a gap between them, you can see this color vision. This is the wavelength range of light. Visible light is the range in between we can see any object our eyes are able to see. So the wavelength range is between, you can see the spectrum now. The wavelength range which it is showing, it is 700 nanometer to 400 nanometer, and the frequency range as you can see in this picture. So this is your electromagnetic spectrum. So, what do you mean by electromagnetic spectrum? Obviously, the spectrum generating due to electromagnetic rays or waves. So, electromagnetic rays are generating when electric and magnetic field both are presented for a wave. Let's see. So, the equations of electromagnetism which we are going to use in this lecture are these four. The first one is what? Gauss law for electrostatics. We have studied it. What was that? That was closed integral E dot dA equals to Q upon epsilon naught. You know the meanings of these terminologies and these terms. Like what is E here? E is electric field. D is the surface area element or the area element. Q is the total charge enclosed in the closed surface, and epsilon naught is the permittivity of vacuum. You know the numeric value also. Second one is Gauss law for magnetism, that is closed integral V dot d equals to 0. The third one is Faraday's law of induction. We have studied it also. Closed integral E dot dl equals to minus d phi b over dt. What is this phi b? Phi b is the flux generating due to varying magnetic field. And the last Ampere's law, that is closed integral B dot dl equals to mu naught I. I is the current. Okay, so for any point in our electromagnetic spectrum, we use these equations to solve the problems. So, who defined these? So, Maxwell was a Scottish physicist, and he established those four famous equations called Maxwell's equations in electrostate, electromagnetism, electromagnetic theory in 1861. So, the equations of electromagnetism are the first one which we will use to make those equations is the Gauss law. So the Gauss laws are for two fields, electric fields and magnetic fields. And you guys know that in electric fields, there are monopole presented, there are dipoles presented, there are quadrupole presented. Okay, but Gauss law for electric field is closed integral E dot dA equals to Q upon epsilon naught. You know this thing. But Gauss law for magnetic field now will be closed integral B dot dA equals to 0, because in magnetic field you know that there is no magnetic monopole. No monopole present, only dipoles are presented. Okay, that is why a presentation or a denotation of single charge, okay, a static charge, is non-imaginary in magnetic field, and that is why this closed integral B dot dA is always equals to 0. So these are two forms of Gauss laws. And next, what we will use to form the equations of electromagnetism is Faraday's law, the third one. So it is closed integral E dot dl equals to minus d phi b over dt. Obviously, you know what does it mean, d phi b over dt. If you change a magnetic field, you induce an electric field. And what will be that amplitude? That will be mod of E. The fourth one is Ampere's law. So close integral B dot dl equals to mu naught I. Now the question is, is the reverse true? Means is mu naught into I is always equal to the magnetic field's line integral? That is always not true. Depends on the position. Okay, now these are the four Maxwell's equations. Please keep all these equations in your mind always, because in many exams, plus most important, in many interviews related to physics, whatever interview you will join, whatever interview you will give in your future, they will surely ask one question from Maxwell's equations. So you should always remember their different forms, original forms, from where they are coming, what laws we are taking, what is their differential form, what is their integral form, what is their physical significance, etc. etc. So all these things you should always remember. Maxwell's equations are quite important with the aspects of exams too. So these are the differential forms of our Maxwell's equations. All the terminologies we will use here are in SI units, System International Units. So the first one is del dot E equals to rho upon epsilon naught, where rho is density of charges. Del dot B equals to 0. Del cross E plus del B or del T equals to 0. Del cross B minus mu naught epsilon naught del E over del T equals to mu naught J, or the last one equation can also be written as del cross B minus 1 upon C square del E over del T equals to 1 over C square epsilon naught J. So we can conclude from the last equation that C square equals to 1 upon mu naught epsilon naught. This is the standard notation. The velocity of light, when scientists used this velocity of light c equals to 3 into 10 to the power 8 meter per second now, then how we can calculate that c equals to this one? So from these two values, mu naught and epsilon naught, we know these values now. So when we are doing this calculation, we are getting c equals to 3 into 10 to the power 8 in SI units. So this is the important result. Now, these are the integral forms of our Maxwell equations. So obviously, the first one is from Gauss law, double close integral E dot ds equals to qv over epsilon naught. This qv is for charge enclosed in whole volume. Second one is double integral close integral b dot ds equals to 0. This is obviously Gauss law for magnetism. The third one is close integral over del sigma b dot dl equals to mu naught I plus mu naught epsilon naught double integral del E over del t ds. This is Ampere's law with Maxwell's addition. You know, this is Ampere's law. Here to here, it is our Ampere's law. And Maxwell edited something and added one term extra here. So this is Maxwell's addition. From where it is coming, there is a derivation. We will not do that derivation here. And the last one is closed integral E dot dl equals to minus double integral del v over del t ds. This is obviously Faraday's law of induction. Moving ahead, let's have an example. I am going to now introduce displacement current. From where it is coming, why we are using that term in the Maxwell's equations. So let's take a look at charge flowing into a capacitor. This is your parallel plate capacitor. Two plates parallelly situated. We are applying magnetic field, electric field is generating, we are getting some output and so on. So this system having this type of equation always, because it is following Ampere's law. So for Ampere's law, close integral b dot dl equals to mu naught I. Now we are doing some changes. If the loop encloses one plate of the capacitor, there is a problem. This was our conventional loop in the first case. But what if it is not our loop? Our loop is this whole area, this one, this light green area is our conventional loop, which is enclosing one plate in the parallel plate capacitor. So what will happen? It will look like this one. It will not have any symmetry. It is looking like a bag. You can see here the last one. It is looking like a bag. Now, can we define properly total flux emerging from this area? We can't define. So there is a problem we are facing. To resolve this problem, what Maxwell did? Maxwell solved this problem by realizing that inside the capacitor there must be an induced magnetic field here in this gap between these two parallel plates. There is a gap now. So inside the capacitor there must be induced magnetic field. Maxwell hypo- hypothesized this and Maxwell wrote an article. Okay, there was not a proved theory. So how he can prove this? Let's see. Inside the capacitor, there is a changing electric field. You know this thing because by this magnetic field, flux is changing, and when we are working on changing of flux, then we can get some induced electric field. Okay, if we are wearing this magnetic field, then this electric field will also change. Again, we can say that when electric field is changing, this electric field will also induce a magnetic field. So on the surface of these two capacitors, polarization will take place. The charges automatically will align themselves in the opposite direction of the applied magnetic field. According to Lenz's law, we know this thing that what the current generates have the opposite direction of the magnetic field applied. So here a current will generate. So that current will be in opposite direction, and using this formula we are getting the relation, this type of relation, close integral b dot dl equals to mu naught id. What is this id? This ID is the displacement current. Displacement current is the current between this vacuum of these two parallel plates in a capacitor. So this was the theory given by the Maxwell, and he introduced some new terms like displacement current, displacement vector density, etc. And he modified basic laws of electromagnetism, and he concluded four equations called Maxwell's equations. So the modified equation will be of this type. You can see here. And now let us derive the displacement current. So for a capacitor, we know Q equals to E naught epsilon naught EA, and we know I equals to dq over dt. Just put the value of Q here. We are getting this one. Now the electric flux is given by E dot A. You know that phi equals to electric field into area. So E dot A. So what we can do, we can put, instead of this E dot A, we can put phi E. We put just phi E, and where this current not being associated with charges, it is called displacement current. So this whole terminology is I, and if we are multiplying this by mu naught, okay, we are not finding any charge in this equation. So when there is no charge, the current is called displacement current. So this is the equation of displacement current. And now close integral B dot dl will be what? Mu naught I was earlier, and ID, I am adding some displacement current also. So what we are getting? We are getting this type of equation. Close integral B dot dl equals to mu naught I plus mu naught epsilon naught d phi over dt. A simple and sweet derivation or definition of displacement current. So these are our four Maxwell's equations of electromagnetism. And we know how this fourth equation is coming now. We have done a small derivation also. So Maxwell did this very precisely, and he was appreciated. Okay. So moving ahead, Maxwell's equations, with time to time, some scientists modified. Okay. So when we want to apply Maxwell's equations of electromagnetism in vacuum. So first of all, what is vacuum? Vacuum is that place there is no charges, no masses, nothing at all, just empty, no air, nothing. So that is vacuum. So in vacuum, if we want to apply our Maxwell's equations, then those four equations will convert into these. So now close integral E dot dA equals to Q upon epsilon naught will become close integral E dot dA equals to 0 because there is no charge. So Q is 0 here. Second one is the same. Third one is also the same. No terminology of charge. The third one will also convert into this one because there, if there is no charge, there is no current. So mu naught I, the term will also vanish. Okay. So these are the four equations in vacuum. Always remember these four equations. Moving ahead. So these were our four equations in vacuum. We have seen this one now. If we want to apply varying electric and magnetic field, varying means we are changing the amount, or we can say amplitude of magnetic field or electric field with respect to time. Like if we are applying on any capacitor for 5 seconds 5 volt per meter, and for another 5 seconds 10 volt per meter, then what we are doing? We are changing the electric field with increasing time now. So the electric field will be varying electric field with respect to the time. So will electromagnetic waves will also change? Yes, they will change. So uh, these two equations we will use for the varying electric and magnetic fields, obviously, because they contain some term of time, dt here, dt here. That is why these two equations we will use to solve the problems, and these two equations can be solved simultaneously. When we solve these two equations, we get these two results. The derivation we will not do here. Okay, obviously, uh, we are not focusing on derivations. We are just focusing on our basics and attempting more and more questions in exams. So, what the result we will get? We will get ext equals to ep sine kx minus omega t j cap, bxt equals to bp sine kx minus omega t z cap. This is j cap and this is z cap. Okay, so these two results we will get. Now we'll talk about electromagnetic waves. So these are our two equations we have to follow. So for the varying magnetic field, these types of current directions we can get. Like this direction of arrow is the direction of electric field, and this direction of arrow is the direction of magnetic field. Okay, if we are doing opposite, we are converting electric field into magnetic field, then the straight lines are showing the direction of magnetic field, which is varying with time, and the curvical directions, these arrows, they are showing the direction of electric field. Some special cases are also there for plane waves. E will be equal to Ey xt j cap. B will be equal to Bz xt k cap. And these two wave equation will satisfy these wave equations. So Maxwell's solution for any wave, for any Maxwellian wave, for any electromagnetic wave, there will be a standard notation. Psi equals to A sine omega t plus phi. This A is amplitude, omega is the angular velocity, and phi is the phase angle. We will learn how to calculate all these things in our question part. Okay, so the basic behind plain electromagnetic waves was these are the two wave equation for electric field. Ext equals to ep sine omega kx minus omega t j cap, bxt equals to bp sine kx minus omega t z cap. So if wave is moving in this direction, this is the direction of wave moving ahead. Just we are just putting it x. Let's see, it is moving in x direction. The velocity of wave is c. It is moving with the velocity of light. If the magnetic field component is in z direction, the red one, then electric field component will automatically be in y direction, because in a electromagnetic wave, electric field and magnetic field are always perpendicular to each other, and they both are always perpendicular to the direction of propagation of the wave. This is the important phenomena. Obviously, I think you guys should have known these things, because these are some basic knowledge of physics. Yes. So the notation for a static wave. Static wave means a wave which is not moving. Okay, which is generating but it is not moving, a static wave. So how we can denote it? It is fx equals to fp sine kx plus phi. Okay, k is equal to 2 pi by lambda, which is wave number, and lambda is the wavelength. But when the wave is moving, like it is moving with velocity v in x direction, and thus at initial time you guys can see that the wave was here at initial time, but after some time the wave has come forward and it is now here. Like you can see this thing, initially it was here, now it is here. Okay, so it is moving. Okay, if it is moving, then it is changing its phase angle too. Initially the phase angle was this one, and when the wave has moved forward, it has come, then the phase angle is changing. So we can change this phi with respect to the velocity. So the equation will be fx equals to fp sine kx minus omega t. What is omega here? Omega is the angular frequency. Omega equals to 2 pi over f. F is the frequency. We can also write a relation between velocity v and omega. that is V equals to omega upon K. Okay. Now, we will study about moving wave. The questions which will come in your exams now, they will always be for moving waves. So just remember this formula. This is this standard formula by which you can calculate magnetic field, electric field and all. So what happens at x equals to 0 as a function of time? X equals to 0 is here on this point. Okay, just put x equals to 0 in this equation. So 0 will be here also. So what we are getting, f0 t equals to fp sine minus omega t. Okay, if x equals to 0 at initial time means t equals to 0, you are putting t also 0, then you are getting fp sine 0. What is sine 0? Sine 0 is 0. So equals to 0. So at this point, x was 0. Initial time, we are not counting the time at this point. Wave was not moving. And that is why the wave equation having the amplitude 0. Okay. But for x equals to 0 and there is something time, t equals to t, then we are getting fp sine minus omega t. Okay, and this is equivalent to kx equals to minus omega t, and from this we can get these types of results. Okay, so the wave moves to the right with the speed v now, and v is equals to omega upon k. Yeah, again, for the same diagram, these are the two relations. These two waves are in phase, like the components of this electromagnetic wave, electric components and magnetic components. If those are at 90-degree angle, those fields are oriented at 90-degree angle, then we will write k equals to 2 pi over lambda. We will use speed of wave this one. C will be, okay, you know these things. And at all times, E will be equals to CV. This is the important result for this magnetic waves, electromagnetic wave. This electromagnetic wave, E will be always equals to CB. When we have given that wave is moving with velocity of light, then what we will do, we will use this formula, E equals to CB. If we have given any velocity like 50 meter per second or so, then what we will do, I will tell you later. So we are talking about plane waves. We know that all the three components, like the propagation vector, electric field component and magnetic field component, all the three are perpendicular to each other. So for these plane waves, these are two important results. Del cross B equals to iota K cross B, and del cross E will be equal to iota K cross E. Okay. So you just note down these results. We will use in our questions. When we will solve the questions, we will use this one. Next, what is pointing vector? Many questions are coming from pointing vector. They are asking the dimensions of pointing vector. They are asking the average of pointing vector. They are asking the average of energy. They are asking the average of radiation. Okay, so first of all, how energy is transferred due to electromagnetic waves, and what is our pointing vector? Let's see that. So on your screen, you can see a equation, that is minus du over dt equals to del dot s plus j dot e. This is called pointing theorem, and it is the differential form of pointing theorem. Okay, this is a renowned part of electrodynamics. Okay, we will just use this theorem to derive this s. This is your pointing vector. So the density of electromagnetic energy has two terms, electric field term and magnetic field term. So you can see that U will be equal to half E dot D, electric field into displacement vector, plus B dot H, magnetic field into magnetization vector. And just putting those values of E and B, you are getting this results too. So this is the density of electromagnetic energy of field, important result. Questions are coming on this formula. Pointing vector S is used to be equal to E cross H parallel to N. What is N? N is the direction, conventional direction. and this is the integral form of Poynting theorem. This equation we will not use anywhere. Just for your information, I have put here. Yes. So if so obviously we know this equation for magnetic field in electromagnetic wave, we know this equation for electric field in electromagnetic wave. We know if wave is moving with velocity of light, this relation also occurs, which is B equals to E upon C. So what are the observable real values? Some real values will be like, if this exponential eta and all this term, we can convert it into sine and cos component. So if we want to write it into cos component, then what we are getting? We are getting B equals to B max cos eta k dot r minus omega t plus delta phi. What is this phi again? Phi is phase angle. And E we can also write as E equals to E max cos eta k dot r minus omega t. Now, we can say intensity or average of Poynting vector will have this result, E square upon 2C mu naught, which also can be written as CB square plus 2 mu naught, which also can be written as CU average. What was your U? U was energy of electromagnetic wave. U was this one. You can see in this equation. Okay, so the important results, this one and this one, always remember these equations. Now this is the conclusion of all those equations we will use while solving our questions. First one is del cross E equals to minus del B or del T. Obviously you know the formula. This is the term of Maxwell equation. Second one is E equals to minus del dot V. Obviously you know this from our first lecture. B equals to del cross A. Many questions are coming on this equation. Third one is E equals to minus del V minus del A over del T. Important relation. Many questions are coming using this equation. Fourth one is B equals to K upon omega n cross E, or also equal to 1 upon V n cross E. In magnetic form, B equals to E upon V. This V is the velocity. Okay, now I told you that when the wave is not moving with velocity of light, and we have given in the question some specific velocity, then what we will use? We will use this formula for amplitude only. Okay, for magnitude only. For the exact value, we will use this formula. I will tell you how to use and how to solve those questions. Fifth is energy density U equals to epsilon E square. Sixth is Poynting vector S equals to 1 upon mu E cross B. And seventh is intensity I equals to epsilon naught by 2 average of E square. Okay, we will use all these formula while we'll solve questions. Starting question is the question 1, and guys, just now listen me carefully, because I have told you that there were many questions. This is the important part, and many questions are coming from this part in electromagnetism, and I am unable to put all those questions in one lecture. That is why I have put here some most important question, and I have solved them with different methods using some basic formulas. So by watching this and listening to me, you will be able to solve some more questions like these questions. Okay, this is really an easy part, and these types of questions are coming for 5 marks in your exam. So please secure your 5 marks at least. So this is your first question. The electric field of an electromagnetic wave is given by. In this question, you have given a term for electric field. The associated magnetic field is. Electric field is given and magnetic field is asking in the question. This question was from NET December 2013, and many questions are coming in exams like this one. They can give you magnetic field and they can ask you electric field. They can give you electric field and they can ask you magnetic field. For GET, for NET, for JEST, and for BARC. This question is must in your paper. So just see carefully how we can solve these questions. So, electric field on an electromagnetic wave is given in our question, that is E equals to E naught cos 0.3x plus 0.4y minus 1000 t and k cap. It is given. A pi is also there, which is also given in your question. So I am just putting a pi. Yes. Now, we know our wave vector. What is the formula? We know that E equals to E naught cos kx minus omega t. This is our used to term for any plane wave. We have seen this now. Like E will be equal to E naught cos kx minus omega t. So this term is our kx and this term is our omega t, obviously. So what is our k? By just observing this equation, we can conclude that our k is pi into 0.3. X means the direction of x-axis, which is I cap, plus 0.4 j cap, the direction of y-axis. Okay, now we know from the question that what is our wave vector. So what will be the magnetic field? We use this formula. I have told you this formula is there to solving these types of questions. You know the K, you know the E, you know the omega. What is omega? Omega is 1000 into pi outside here. So 1000 pi. Just put all the values, do some mathematical, and you can get these results. So you are getting this one, and you can see that the correct answer is this one, 10 raised to the power minus 3, 0.3 I cap plus 0.4 j cap E naught cos pi 0.3x plus 0.3 y minus 1000 t into k cap. So this will be your right answer, and according to this, correct answer is B, but I cannot see the correct answer is B because here is 10 raised to the power minus 4. There must be some mistake. It is 10 raised to the power minus 3 here. Just remember the recipe to solve. If you have given electric field, how you can get your magnetic field? If you have any query, you can ask me in mid between also. Just stop me and ask me whatever you want to ask. Okay. So moving ahead, this is our question number 2. A plane electromagnetic wave is traveling along the positive z direction. The maximum electric field along the x direction is 10 volt per meter. If in question one is saying that maximum electric field, that means the amplitude is given. The value of E naught is 10 volt per meter. The approximate maximum values of power per unit area and magnetic induction. So the question is asking to calculate power per unit area and B, magnetic induction. Two things we have to calculate here. This question is from NET June 15. So yes, we have given E equals to 10x. I have told you this is amplitude only. So we will use the formula of amplitude. So this is the formula to amplitude to calculate the amplitude. So B will be equal to E upon C. E is given in question and C you know. So you can calculate. So B will be 3.3 into 10 to the power minus 8 Tesla. Okay. So in those four options, obviously there is only one option having 3.3 into 10 to the power minus 8 Tesla, but we will see for power 2. Power per unit area is your pointing vector, and the formula is S equals to 1 upon epsilon naught E cross B. You guys know that amplitudes are given, so we will use in amplitude form. So amplitude E, amplitude B, sin theta upon mu naught will be there. Maximum power is asking in our question now, maximum values. See here, maximum values. So maximum means the maximum value of sin theta. So theta will be at 90 degree and sin theta will be maximum. So we will use theta equals to 90 degree. Just put the values and solve the question. So the S we will get 0.265 watt per meter square. Option D will be correct, obviously. Easy question now. And the
Ma'am, can
easiest
I
method,
question?
yes, yes.
Ma'am, in this question that we get the 0.265 watt per meter square, but this calculation in CSIR net is not easy because there are no calculator. How can we do that?
You can just this is quite easy calculation, buddy. You can just solve these calculation. You are allowed to use pen and paper now. So on your paper,
Yes.
you can solve this. This is not a difficult calculation. You can solve this. I think you can solve this. The value of pi you know na, 3.14, or you can use 22 by 7. So 7 will be here. Some powers you have to calculate, so you can easily calculate. There is not a tough calculation. Okay. In your net exam, tough calculations will not come. Honestly, I am speaking. Okay. So don't
Okay, ma'am.
afraid of doing some easy calculations.
Ma'am,
The third, yes, yes,
ma'am, in
yes.
this question, mu 0 is equal to 3 into 10 raised to 8. This value is correct or not? Why here putting mu 0 is equal to 3 into 10 raised to 8?
No, they are not putting the value of mu 0 here. This is
Okay.
your E. This 10 is your E.
E.
And this value is your B, na? See,
Okay.
this is your value of B,
Okay,
isn't
means
it?
here is yes, yes.
And this is our 1 upon mu naught.
Okay. Okay.
Na? Don't be confused.
Okay.
Chaliye. Okay, moving ahead. This is question number 3. Suppose the y-x plane forms a chargeless boundary between two media of permittivity epsilon left and epsilon right, where the ratio of epsilon left and epsilon right is 1:2. If the uniform electric field on the left is which is given, where C is a constant, then the electric field on right will be. Okay, we have given electric field on left, we have to calculate electric field on right. One condition we have given, that is we are using y-x plane. Okay, so just make a picture. This is your y-x plane. This plane is your y-x plane. Okay, in this plane there is a boundary between two media. Let's suppose this is your boundary. Okay, this is your boundary, and this is your E left, EL I am writing, and this is your E right, ER. Okay, this one is given and this one is asked into exam. So how to solve these types of questions? So this question is basically from NET June 2015, and frequently these types of questions are coming year by year. In NET June 2019, the same question has come. In NET June December 2019, a question was related to this problem, but not the same. Something was related. So how to solve these types of questions? Apply boundary condition. Okay. What are our boundary condition? In the lecture of electric field, I think lecture number 4 or 5, here we have studied about boundary conditions on electric field, because we have given the components of electric field, na? So we'll use boundary conditions of electric field, that were E parallel above equals to E parallel below. Second boundary condition was D perpendicular above minus D perpendicular below will be equal to sigma f. Okay, it is saying that in this question there is a chargeless boundary. If there is no charge, then sigma f is 0. Chargeless means no charge, no free charge, sigma f 0. So this D perpendicular above will be equal to D perpendicular below. Okay, we have given plane is YZ plane. Okay, this is YZ, not YX. And this is our Z, this is our Y. Okay, YZ plane. So Y and Z axis are parallel to plane. Okay, so if Y and Z axis are parallel, then we can put J cap and K cap same, because Y and Z axis are parallel. Just X axis will change, so the values on X axis will change, not on Y and Z. Okay, now we will discuss perpendicular component. Epsilon E perpendicular above will be equal to epsilon E perpendicular below. So E perpendicular below will be equal to this one. This ratio is given in our question. That was 1:2. Just put the ratio and finally we can get the result. So E for the right side will be equal to C I cap by 2 plus J cap plus K cap. Most easiest question we can do. Nothing we have done in this question. So these types of questions are coming. The next one, the electric and magnetic fields in the charge free region Z greater than 0 are given by ERT equals to E naught exponential minus K1Z cos K2 x minus omega t j cap. BRT equals to E naught over omega exponential minus K1Z K1 sin K2 x minus omega t I cap plus K2 cos K2 x minus omega t K cap, where omega K1 and K2 are positive constants. The average energy flow in x direction. Average energy flow means to solve pointing vector. So E is given, B is given, pointing vector, you know the formula, S equals to E cross B or mu naught, and we have asked in question x direction. So we will use only x components. Yes, by using x components, we are getting these results. Now, we have to calculate average now. So just these all are constants. So we can't use average on these. We will just use average on cos. So always remember the average of cos square theta and sin square theta is always equal to 1/2. Just note down this thing. Average of cos square theta and average of sin square theta. Both are equal to 1/2. So at last we will get these results. Average of S will be K2 E naught square exponential minus 2K1Z upon 2 mu naught omega. Correct option will be option number A. This was also an easy question. Question was from NET June 2015. Next question. Consider the interference of two coherent electromagnetic waves whose electric field vector are given E1 this one and E2 this one, where phi is phase difference. The intensity of this given two electric field is given by this, and where average of E square is time average of E square. So we have to calculate the total intensity. Now, this is a different type of question. We have given two components of electric field and we have to calculate the total intensity. This question is from NET June 2012. So how to solve these type of question? If two components they will give now, then just add them up. Use law of superposition. So the total electric field will be equal to E1 plus E2. The formula of intensity we have given in the question, that was I equals to epsilon naught by 2 average of E square. Now we can conclude from here that average of E square should always be greater than 2 E naught square. Obviously average will be greater than to the amplitude, but it will be double to the amplitude only if there are two different components given in the exam. Remember this line. Average of E square will be always greater than if there are two different components of electric field. Okay, so there will be no effect of phase on average value, and that is why just we will put this 2E square here and we will get E naught epsilon naught E naught square. So the correct option will be option number B. Okay, moving ahead. Question number 6. Again, a different type of question. The space-time dependence of electric field of a linearly polarized light in free space is given by x cap E naught cos omega t minus kz, where E naught, omega and k are the amplitude, the angular frequency and the wave vector respectively. The time average energy density. What we have to calculate? Time average energy density means energy density and average of that energy density. Okay, we have given only one term, that is x component of electric field. So we will also calculate only density term in the form of electric field, in the terms of electric field only. So we will use this formula U equals to half epsilon naught E square. Half epsilon naught we have put and the value of E square. Now we have to calculate the average. So you guys know now what is the average of cos square? The average of cos square theta is always 1 by 2. So the answer will come 1 by 4 epsilon naught E naught square. Option A will be right one. Easy question now. This was from GAT 2012. Again, one more question. This is another type of question. A plane polarized electromagnetic wave in free space at time t equals to 0 is given by E x z equals to 10 j cap exponential eta 6x plus 8z. The magnetic field is given by electric field is given and we have to calculate magnetic field. The same question we have done in question 1. We have used this formula B equals to 1 upon C K cross E. So what is K here? Just observation. You can conclude that this is your value of K and omega is obviously 0 because there is no term with time. No coefficient of time. So omega is 0. So just use this formula. But the difference is for K cap, you will convert this K cap into K over K mode. Mode of K is 10. 6, 6, 36, 8, 8, 64. Under root of 100 is 10. Na? So this is your K cap. This is your electric field which is given in your question. And you can get these types of results. Okay. So there was no omega in electric field. Here is no omega. But rather than we are getting some omega value in our magnetic field. So this is significant importance of these type of questions. Correct answer is option number A. Next question. Consider a solenoid of radius r with n turns per unit length in which a time dependent current I equals to this one, I naught sin omega t, where omega r over c is less than 1 flows. The magnitude of electric field at perpendicular distance r less than r from axis of symmetry of solenoid is a different type of question. Time dependent current is given. We have to find the magnitude of electric field. Magnitude of electric field. You guys know na the concept of solenoid. In the solenoid, we know that there is always a magnetic field. So current is given, magnetic field is always there in the solenoid. So we can calculate the electric field na. So we will use this formula. Line integral of E equals to minus d phi over dt. What is this phi? Phi is magnetic flux. What is this phi? Phi is B dot ds. You know this thing. So now for solenoid, just note down the formula. This is your magnetic field in the solenoid. You know this thing. In previous lectures, I have told you B equals to mu naught n I. Mu naught and I naught sin omega t. I am putting this I naught sin omega t because we have given in the question I equals to I naught sin omega t. And this dl means length. We know that solenoid has a cylindrical shape. So the length will be 2 pi r. So E dot 2 pi r will be equal to this one. Just you will solve this and you will get the results. So this is a different type of approach to get electric field for any magnetic material. If this question will come for toroid, then you will use the formula for toroid. If this question is coming for two wires carrying some current and generating magnetic field, then you have to use that formula of magnetic field. Okay, and so on. You can calculate the electric field. So this question was from CSIR NET December 2011. Okay guys, there were many questions, but I can't put them all in one lecture, and that is why these 8 questions were of different types, and that is why I have come those questions for you. I hope This was an important lecture and you guys can grasp more and more. So if there is any query, you can ask me.
Ma'am, if you say last question one time, it will be help.
Yes, yes, sure. This is our last question.
Yes. The main problem, if you say one time more.
Okay, you want me to explain this again, na?
Little.
Okay, okay. Just read the question. We have given a solenoid having radius r having n turns per unit length, and there is a current which is depending upon time. Why we are saying that it is depending upon time? Because there is a time term. This is sin omega t. Okay, that is why we are saying this current is depending upon time. So I is equal to I naught sin omega t for that solenoid, and the magnitude of electric field at a perpendicular distance from the axis of symmetry. Okay, there is no role of this position. R is less than R. Okay, no role of this because we are not going to find the magnetic field at particular point. We have to calculate magnitude of electric field. Na? So we'll not use this. Okay, so this was a formula from your Faraday's law. Integral of E dot dl equals to minus d phi over dt. This phi was magnetic flux, and we used to write this phi as equal to B dot ds. B is amplitude of magnetic field and ds is elementary area. Okay, so for solenoid we use this term of magnetic field. We know that for a solenoid at any point there is a magnetic field B equals to mu naught and I, and just put the value of I which is given in your question, that is I naught sin omega t. So mu naught and I naught sin omega t, it will be, just put this value of B here. So you will get minus del over del t integral mu naught and I naught sin omega t into ds. You will get this one. Okay, so this E dot dl is equal to this one na. So dl is your elementary length, and integral if we want to apply, then we will use the full length. Okay, so the solenoid is a shape of cylindrical type, so we will use 2 pi r obviously. So E dot 2 pi r will be equal to this. Just do one time derivative with respect to time, and you can get these results easily. So
Okay.
obviously you will get correct answer D. Okay, any more queries?
No, ma'am.
Yeah, I
No,
will put some short notes by tonight or maybe early in the morning tomorrow, and I will put an assignment on this magnetic field and Maxwell equations. So please do those assignments and review those formulas so that you can grasp more and more. So all for today. We'll see you in. I'll see you in next lecture. Thank you.
thank you, ma'am.